All right. So first, some stylized facts about the return of stock market. So this is for U.S. Most finance research is about the U.S. market because it's big. It has a very good data. So most of the research you see will be about the U.S. market. So this is the real stock and bond performance, that is, net of inflation, right? Real stock and bond performance over time in the U.S. from 1926 to 2005. The blue line with square markers is the stock market. The pink line or purple line, it's the bond. It's the government bond, U.S. government bond. Now, if you just look at a short period of time, sometimes the bond market actually does pretty well relative to the stock market. But over the long run, if you talk about when you talk about things like 20 or 50 years, the stock market just returns significantly more return than the bond market. In the stock market, when you're talking about stock, the risk premium is called the equity premium. The equity premium, because stock is also called equity. Right? Equity premium. So this is the equity premium over 20 years period. So it's asking if you buy stock at a certain year and hold it for 20 years. It's the other way around. Sorry, because if you buy stocks 20 years early, what do you get at that year, right? So it's essentially the same data as before. So ending at year 2000 here. So if you buy a stock 20 years ago and sell it today, and this is today, what do you get? Pretty much in any year you pick, you get a positive return over bonds. There are some periods, if you're familiar with U.S. history or world economic history, during the oil crisis, the return on the stock market is relatively low. But otherwise, as you can see, the return is even during the oil crisis, it's still positive over bonds. Okay? And at times it's very high. So during right before the dot-com bubble, as you can see, it starts going down because the dot-com bubble is coming. But even right before the dot-com bubble, we're talking about a premium of 12% on average. 12% on average. So it's a lot of money we're talking about. And it's always positive. What this says is, what is so striking about this is, if you're actually investing for 20 years, which most of we do for at least our retirement return, there's no reason not to put them in stocks. In fact, there's no reason not to put all your retirement savings in stocks, because based on past records, you almost can never lose out. Now here's the problem. Assuming that average U.S. investor has a CARA utility and normalized wealth to 1. Now, whether that's theoretically correct, it's another issue. To begin with, as we say, this is not a very good utility function to describe people's behavior because people have different wealth. But let's just, for the sake of argument, assume everyone has a CARA utility. And as we know just now, the solution to the CARA utility is the dollar you want to invest in stock equals to the excess return, equals to the equity premium, excess return. There are a lot of names for the same thing. Excess return over your risk preference times variance. Average excess loss return from the previous diagrams is about 7%. So you can expect in a typical year, on that you would get 7% more return from the stock market over government bond. So for example, when government bond is returning 2%, you can expect 9% on average. Now we're talking about averages over 20 years, not over like 2 years. If you're looking at this year, it's worse than bonds. But over 20-year period, you get about 7% premium. Standard deviation is about 15%, so it's quite variable. Now, assume that the U.S. investors have 30% of their wealth in stock, which is higher than reality. In reality, it's lower than that. So, remember, we normalize wealth to 1. So they have 30% of their wealth in stock. So that's 0.3. Return is the risk premium, which would be equity premium in stock, which is also called excess return. So 0.07. Okay. A is something we want to estimate because we want to know what people's risk preference is, and the risk is measured by standard deviation squared. That gives us the variance, right? Okay. So rearranging, what do you get? A is about 10. Now, just looking at this, there's nothing that strikes you as problematic. But if you put A equals to 10 back to a utility function and ask what this individual would do in other situations, then it becomes problematic. So if in A equals to 10, how risk averse is an investor with A equals to 10? Now, imagine we give the investor the choice of getting an additional 50% of our current wealth for sure. So it's a sure thing. I'm going to give you the money now, 50% more, no risk. Versus a 99% chance of getting X% more and 1% chance of losing 1% of your wealth. And you can ask, how large does the X% has to be to induce her to choose the second option? What do you think? What would be reasonable? What would you choose in this case? In one case, you get 50% more wealth for certain, right? So it's a safe option. In another case, I say you have a 99% chance of getting any amount of additional money you want. But there's a 1% downside. You might lose money. What value will you pick? What do you think? 55. Wow. Okay, 55. Who else? What do you think? What will you pick? But just guess. If I say, if you give you 50% more wealth, but in other case, I will say, there's a chance that you could lose some money. How much more money do you want? Would 100% be enough? 5% is already okay. Okay, so wow, you guys are very, very averse. Okay, so there's math involved. So there's a lot of math involved. But without going, you can look through the details yourself. But if A equals to 10, the investors would choose the safe option even if we offer infinite wealth. Which, as you just see, is just not realistic because two of you are willing to take 5% more in return for the 1% risk. But expected utility theory would say that an investor with CARA utility with an with a rate of absolute risk aversion of 10 would not take any amount of wealth over the safe option. Which leave us a few options. One, this is just a very bad utility. Two, maybe the parameter estimation is not very correct. It's not quite correct. Okay. Edward Prescott, which won the Nobel Prize, he has a very famous paper called the equity premium puzzle. So this paper is famous because it showed that with CRA utility, you have a similar problem. Now, CRA utility mathematically is harder to derive, so we're not going to go over that. But you should trust Prescott, right? I mean, he won the Nobel Prize. So if you use the CRA utility and conduct the same exercise we just did with CARA, same exercise, and you can plot the range of equity premium that would induce investor to invest in the amount of stock we see. It's just not very realistic. So what you will see is this. Okay, so this is the average risk-free rate on the horizontal axis. One thing I really like is that this paper was published in 1985, and notice that the diagrams are all hand-drawn. Can you imagine that today? It's actually very nicely drawn. Like, can you draw, like, the numbers are written so nicely. Yeah. Although these days, probably no one would use this font. This looks like Comic Sans font, which you not use in academic writing these days. But, so this is the average risk-free rate. That's the average risk premium. As you see, they are like, basically they all mean the same thing. Risk premium, equity premium, excess return, they all mean the same thing. Okay, so what this diagram is showing you is that if based on estimates from either logic or other source of information, there's a very tiny range of region in which investors would invest in just so little stock as we see. What it says is that you need about something like a 0.3 or 0.4 risk premium in order for investors to invest so little in stocks. If you have something as high as 1%, you would expect people to invest a lot in stock. Because remember, over 20 years period, there's very little risk in investing in the stock market. Now, and as I just said, based on the diagrams we had at the very first two slides, the average risk premium over 20 years is like 7%, which would mean that everyone should invest in stock. Okay, so this is why. This is called the equity risk premium. The equity risk premium, you can interpret two ways. So the problem center to this phenomenon is that existing investment patterns suggest an implausibly large rate of risk aversion. This is the exercise we just did. It was very simple calculations, probably too simple to be realistic, but still, you get an estimate of risk aversion. And it's very high, too high to be realistic. But you can also see it another way. Put it in another way. Given the existing return and risk involved, investors are investing too little into the stock market. And the second way of looking at it is more helpful because it makes you think about what factors are stopping or preventing investors from investing more. Okay. So there are few potential explanations. One of the explanations is that maybe we are not observing some people's wealth, especially those who are not investing in stock at all. Now, what do I mean by that? For example, let's just say only half the population is investing in the stock market, and the proportion of wealth in the. So what does that mean? That means that instead of everyone, so you see 30% of the U.S. wealth is in stock market. So one possibility is everyone is investing 30% of their wealth. Another possibility is you have 50% of people who are not buying any stock for some reason. You have 50% of the people who buy stock, and because 30% of the country's wealth is in the stock market, you can conclude that on average, you have those people who invest in stock are putting 60% of their wealth in the stock market, right? So if you are not observing everyone's wealth, so you would be understating how much money, the proportion of money that is in the stock market. Okay? And no data is perfect, so this is possible. So suppose now we adjust it to 0.6, A becomes 5, which is significantly lower than before. But we would need a really huge amount of unaccountable wealth to get a reasonable ARA of 1. Now, why is this reasonable? Once again, this is pretty much based on the calculations we have previously. And so essentially the problem is for people to ignore such high returns, they would do very crazy things when you give them small returns. And in real life, there are many things that with very low return that people still do. So ARA, what we believe to be reasonable after the rate of risk aversion is about just 1. So they are slightly risk averse. That allows people to still take on some risk. Okay. So it's just very difficult. You are talking about you probably need to be unable to observe most wealth in the country to be able to use this simple formula to explain. Yeah, this is cumulated 20-year invest equity premium over period. This is the realized premium per year. Okay, per year. So the previous diagram shows you the risk premium if you invest 20 years, take it out, divide your return by 20. This is what you get if you invest today, take it out in 1 year. So 1 year risk premium. And it fluctuates a lot. This once again shows you that long-term investment smooths out your return. Stock market is only safe if you invest for long term. Even if you're investing for a whole year, which to many investors in the retail market, that's already very long. You still have like a pretty high chance of losing money, and as much as 50% in some cases, right? This is the Great Depression, stock market crash. This is the oil crisis and dot-com bubble. So if you invest in only a single year, there's a significant risk. So now here's something that I would say is very quite central to behavioral economics. Look at this diagram. Just if I haven't shown you the previous diagram, would you have been able to deduce that the stock market is actually quite safe over the long run? Probably not, right? If I just show you this diagram, you would think the stock market is very risky. You would see that there's almost half chance of losing your money and half chance of gaining. So that's extremely risky, right? So one thing that behavioral economists have found is that the way you show return would significantly affect people's investment behavior. If you show them aggregate return, they are much more willing to invest than if you show them short periods of return. Okay? So if you see this diagram, it looks very risky, and unfortunately might not be the right word, but in real world investing, most of the return data is shown year by year, or even shorter period, right? If you log into your stock account, you get day by day, minute by minute return. And the shorter you go, the more risky the stock market appears. Virtually no one ever see a 20-year return distribution. So with this idea in mind, maybe investors don't think in the way expected utility requires them to, because expected utility requires you to bring in the aggregate. If you're thinking about investing for 20 years, you compare the average return from stock over 20 years to the average return of bonds over 20 years. You don't compare year to year because it's not meaningful to what the question at hand, which is what you should do over 20 years. But maybe investors don't behave according to expected utility. Now, suppose investors are short-sighted. They only consider short-term gains and losses. Graphically, just think about the previous diagram. That's what they have in mind. Short-sighted. Second, making a loss is more painful than not making an equivalent gain. So people really hate losing money. Really, really do. This is called myopic loss aversion. Myopic for short-sightedness, and loss averse refers to the hate of loss. Loss aversion is center to the field of behavioral economics. This is arguably one of the first major findings of the field. That's that people are loss averse. If I give you $10 and then take away $10, it's not going to be it's not necessarily going to cancel out. Yeah, it really depends on the situation. It depends on the situation. So generally, when people lose money, they feel a lot more pain than the happiness they get when they get an equivalent amount of money. So, in the eyes of myopic loss-averse investors, the stock market is very risky because they are looking at a short-term return distribution. And because they hate loss a lot more than they like gain, when you have almost a half chance of losing money, they're not going to invest at all. They're not going to invest at all, not even a small amount. Because if you now not investing, you are isolating yourself from any chance of losing money, right? If you only invest a small amount, you're exposing yourself to the possibility of losing money. And as we'll see in a moment, the feeling of losing money, even a small amount, is very painful. So in some sense, you feel the pain from losing, not from the amount. Losing is losing. And losing any amount feels very painful. If you think about it, it does make quite a lot of sense, right? Let's say you drop a $100 bill. You lose a $100 bill. It feels so painful. But like in these few months, I probably lost like thousands or tens of thousands of dollars in my retirement account. I feel nothing, right? So the sense of loss is much stronger than the effect of the amount itself. And why would the investors have to be myopic? As I said, because most real-world stock return information comes in short duration, right? If you invest in, say, something like MPF or any mutual fund, they send you yearly reports. So you naturally would be looking at yearly returns because that's what the company offers you. If you invest in your own stock, you'll be seeing daily returns, hourly returns, or minute returns. The stock market is extremely risky if you look at it that way. In the U.S., and I think not in Hong Kong, but in the U.S., in U.S., when you lose money on the stock market, you can actually use it to reduce your tax payment because that's a capital loss. So so that's why people have a very strong incentive to calculate their gains and losses every year, because you can actually use it to reduce your tax. In Hong Kong, I don't think it actually matters. If you can make millions of dollars on the stock market, you pay nothing in tax. Yeah. So, what evidence there are on loss aversion? Oh, wait a minute. It's 10, right? So I still have many hours. When do we stop? 11:15? Oh. Okay, let's take a break, and then we'll come back to talk about the loss aversion. So we start again in 10:25? Yeah, 10:25. All right, evidence on loss aversion. Okay, so this is psychology. Which circle is bigger? Now, I'm not asking you about this one versus this one. I'm asking you about this one versus this one. Now, okay, whenever you see a question like that, you know the answer is the same. But, or to be honest to yourself, right? The one on the left should look bigger. Huh? Okay. This is why psychology experiments are not necessarily reliable, because you get into this situation where people start guessing what answer do you want them to answer. But the idea is human perceptions are comparative. And it's easy so for example, it's easy to tell which of two buckets of water is warmer. This is a very standard example in introductory psychology. It's very easy. If you have two buckets of water, one is warm, one is cold, it's very easy to tell which one is warm and which one is cold. But it's very difficult to tell the absolute temperature. In particular, if you have a bucket of cold water versus a bucket of ice water. If you dip your finger into the ice water and then dip the same finger into the cold water would actually feel warm. So this is something you can try at home if you want. But it will feel warm. So human perceptions are relative. And similarly, gains and losses in wealth are more pronounced than absolute change. What you remember is you lose money, whether you lose money or you gain money. The amount that you gain or lose might not actually be that salient. So this experiment is a very famous experiment. It's conducted by Kahneman, who won the Nobel Prize as a psychologist for his work in this area. An experimenter randomly assigns subjects to three groups: group 1, 2, and 3. So to group 1, he gave a candy bar. To group 2, he gave a mug, while to group 3, he gave nothing. So, group 1, candy bar. Group 2, a mug. Group 3, you get to choose. So, he then tells the first two groups that they can exchange what they were given for the other good. Group 3 can choose whatever they want. They can either get a candy bar or a mug. Now, what do you expect? It's very hard to give. Obviously, it's going to be very hard to give me a number just by the setup. But let's just say, you observe group 3 first, and you see that about 50% of the people choose the candy, and 50% of the people choose the mug. How many people what's the proportion of people would you expect would change to candy in group 2? Well, since you see half the people want candy, half the people want mug, and the assignment into groups are completely random, you would expect about half the people would want to switch to candies. Similarly, in group 1, you would expect half the people would want to switch to a mug, on average, over many people. Is that what happened? So, okay. No. The actual distribution looks as follows. For the group 1, which they were given a candy bar, only 11% want a mug. 89% wants to stick with the candy bar. For the group 2, where they were given a mug, 90% want to stay with the mug. 10% wants to stay with the candy. Wants to switch to candy bar. And for the group that's given nothing, as I already mentioned, it's about 50-50. Notice that the pattern here, right? A striking similar is that about 90% of people want to stick with what they have, and 10% want to switch. I've done this, I think, either last year or the year before, in class, when there are more people, with M&Ms. I think I give them choice of milk chocolates versus peanut chocolates, something like that. And you get a very similar pattern. Most people would stick with what they have. And I think in another year I've tried with candy versus pens. Similar. People like to stick with what they have. This observed pattern is called the endowment effect. It's very common. And the interpretation is, how do you interpret, right? People want to stick with what they have. Now, I think one very direct interpretation is people are lazy, right? They don't want to do anything. So you give them the ticket and they want to just wait till they leave. But usually experiments are very careful in trying to avoid situations like that. Like, for example, even if you don't exchange, you have to do something else so that you are still exerting some effort. So experimenters try to be very careful in minimizing all other explanations. So, and that effects still remain. So the interpretation here is that the subjects who got the mark felt losing the mark as a loss. So you have a mark, you hold it in your hand. If I want to take it away, you feel like you're losing something, right? Okay. So you're losing a mark, and you're gaining a candy bar. Now, the mark is already in your hand. The candy bar is not. So you can argue that it feels different. You have something in your hand, you rather keep it, and instead of getting something that you don't have. Subjects who were given nothing to start with only see that as a forego gain. You don't have a mark in your hand, you don't have a candy bar in your hand, so you're not really feeling any sense of loss. You're not losing anything in your hand. So it feels like this: mark or candy. Whereas if you already have a mark, it feels like losing a mark, adding a candy. And what we're saying is these two situations are different. These two situations are different. The losing has a very profound effect. So, right? Remember how I say I was happiest when we had nothing. It was saying like this guy probably lose all his money in the stock market. So now, I would say that this concept is called loss aversion. It's pretty much it's a current standard. We believe that that's what people have in their mind. When you take away their mark, they feel a loss. When you give them something, they feel like a gain, and gain is not as important as a loss. It's not settled. There are other explanations possible. For example, if you think about it once again, there are other possibilities. For example, the mark is in my hand, but the candy bar is not. How do I know that if once I give you your mark, you're going to give me my candy bar? Maybe you're trying to trick me. Trust in the experimenter is a very important issue. So in economics, at least, we typically do not allow deception in experiments, because once you start tricking people, then they will start losing confidence in you, and they don't believe what you say, right? So it will mess up not only your experiment, it will mess up future experiments. So in economics, there's a very strong ethic rule that you're not supposed to deceive. Not so in psychology, right? There's a very famous psychology experiment. I'm not sure whether we're going to get to talk about it later on, so I'm going to talk about it now. Actually, there are two. So the first one is the first one. Is it called Milgram experiment? I don't remember. The first one is one where some researcher invited people through a newspaper and magazine to participate in an experiment on electric shocks. So the experiment works the following way. Let's say I invited you, right? I invited you to participate in the experiment. You come to the experiment, and I ask you to take a seat. There is a panel of buttons in front of you. And then, in another room, separate by a glass window, there's another person sitting. You were told that he is another subject, and you are both participating in an experiment of electric shock, the effect of electric shock on people, right? So the buttons in front of you ranges from something like harmless 1 volt to like absurd 400 volts, okay, with a word danger in front of it, okay? So it's red with the word danger. And then me as experimenter, I'm going to ask you to start clicking the buttons, right? So you click, start with 5 volts, you click, and then he's like, no, he's like just get shocked. And then I ask you to increase the voltage gradually, right? 5 volts, 10 volts, 50 volts, and so on. And you see that the person in the other room starts getting more and more painful. Now, you can't talk to him because he's in another room, separate by a glass window. So, but eventually, he looks really painful. And what would you think at that point? You would try to stop, right? You think. But, so you say, you might ask me, can we stop? Then I'm, as an experimenter, wearing a lab coat, right? I'm going to say, keep going, it's all right. Now, what do you think most people would do in this case? Since it's an actual experiment, what do you think most people did in this experiment? Do you think they continue or did they stop? Continue. That's right. Most people, the vast majority will keep continue, despite the fact that if you actually know anything about electricity, 400 volt would kill that person. Still, most people would click it, because the experimenter in the lab coat told them so. Now, this is deception, because turns out the other person in the room is an actor. He's just pretending to be shocked. The buttons have absolutely no effect. Okay, so this experiment would probably not be allowed today, because it's very strong deception. It has very negative psychological effect on the subject, right? Think about the guilt they have if they didn't know that this was actually an actor. So this experiment would probably not be allowed to run. Another very famous experiment is called the Stanford Prison experiment, in which the professor in the Stanford psychology department turned the basement in their building into a makeshift prison, and they have the cooperation of the local police. So what they did was this: they recruit subject in they told them it's like a simulated prison experiment. Right? It's a psychology experiment. They recruit subjects. They have the local police helping to make it very realistic, actually arrest the subject and bring them to Stanford, lock them into the prison. And so what they want is to look at what happens in such a closed environment. So half the subjects were prisoners, and half the subjects were prison guards. Right? They are all Stanford students. Okay, Stanford students. The prison guards were supervised by the professor, so he acts as the warden of the prison. Now, this experiment was very famous because it went really badly. Because as the experiment progressed, just a few days into the experiment, the students acting as prison guards actually act like prison guards, and the students acting as prisoners actually became like prisoners. What that means is that the prison guards actually start I would say not physically torturing, but like psychologically torturing the prisoners, like ask you to do sit-ups, like verbally abusing you, and not like that kind of stuff. It went so bad that it took another professor to stop the experiment, because the professor responsible for the experiment was so involved himself. The professor started treating the subjects as prisoners. So it took an outside professor to stop the whole experiment. So this is a very famous experiment. This is a very famous incident, and once again, this experiment would not be allowed to run today. Okay, I should be careful today. This experiment would not be allowed to run in the U.S. today. In Hong Kong, not so sure. We have very lax regulation. So maybe you can run an experiment by turning ELB into a prison. But generally, these days we do not deceive subjects. So just to prevent the situation where subjects don't believe in you. So they think, oh, I'm going to keep my mouth because you're not going to give me your candy bar. Now, mathematically, you can model this behavior in a very simple way. is that you have a certain reference point. Your utility now depends on both what you have and your reference point. Now, what the reference point is something we talk about later on. But just so in this current situation, let's just say that your reference point is what you have with you right now, what you get. X is X is something you have to choose. So, for example, if you expect to have a mark, what's your utility of having a mark? X, so you expect a mark, R equals to 1 mark. X is the actual number of marks you're going to choose. And so if you expect 1 mark, R equals to 1, and you choose to have 1 mark, X equals to 1, your utility is 1 minus 1 equals 0. 0, because you're not gaining nor losing. So that's the idea of gain and versus loss. You're not gaining nor losing. If you expect 1 mark, but you get 2, you get 2 minus 1 equals 1. Because you expect 1, you get 2, you're gaining 1. Okay. What if you expect 1 and get nothing? Then you have, because 0 is more than 1, you get phi multiplied by 0 minus 1. So it's a negative number, and phi is going to be bigger than 1. So what does that capture? It captures the asymmetric effect. When you gain, you get X minus R. When you lose, you get something like 2 times X minus R. This captures the asymmetry. Gain is not as important as losses. So V is estimated to be approximately 2. How? Mostly by experiments like the previous one with money, right? You see what you ask people to buy and sell stuff, and you see how much they are willing to pay to buy an item versus how much they're willing to sell an item. Usually they're not the same. If you want to, if you think about whether there are any examples in your real life, you can it's not easy to make something that is completely directly available. For example, if I use cell phone as an example, now if I ask you how much are you willing to pay to buy your cell phone versus how much you're willing to pay to sell your cell phones, it does fit this pattern, because you probably want, if the cell phone is new, you're probably unwilling to give up your cell phone in order to exchange for versus, so you probably want more money if I ask you to sell your cell phone versus the amount you pay to buy. But that's because it might be because it's inconvenient. You lose your cell phone, you have no cell phone to use, so you want a lot of money to compensate for that. So it's not necessarily due to simple loss aversion like this. So but in a lab experiment, when I give you something which you do not have previously, and you're telling me you're not unwilling to part with it, then that's a very strong indication that you don't like losing things. So in the assignment 2, later on, you would see you have a numerical question that shows you what's the effect of phi equals to 2. So, but the intuitive interpretation is loss is twice as painful as a forego gain. So, one very good example is money. Money would be a good example. What they say is this: if I tell you if I give you $10, then I take it away, you might feel a bit unhappy. But if I take $20 out of your pocket directly without giving you anything to begin with, then you would hate me twice as much. So that's what it means. So we'll leave the question of reference point should be for later. But here are going to be a series of questions that allows us to investigate the properties of loss aversion. First, if I ask you to choose between losing $500 for sure versus losing $1,000 with probability half and losing nothing with probability half. Which one would you choose? Notice that the average is the same, right? In one case, you're losing $500 for sure versus losing $1,000 with half chance and losing nothing with half chance. All right. How many of you would pick the first one? 2. So how many would be? So the rest would be picking the second one, right? Okay. So, right. Let me write it down. 2 versus 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. What about these two? Gaining $500 for sure versus gaining $1,000 with half chance and gaining nothing with half chance. Once again, the average is the same, but one is risk-free, one is risky. Now, how many of you picked the first one? 1, 2, 3, 4, 5, 6. 6. Okay. So now, okay. All right. Now notice that by the fact that quite a few of you hate risk, avoid risk for gains, but seek risk for losses, means that there's not a constant risk aversion over your whole range of wealth, right? Because when I ask you about gaining money, you say I would prefer the sure thing versus the risk. But then when I ask you about losing money, most of you prefer to take the risk. Okay. So this is actually it is actually the right, I would not say the right thing, but it's the common thing. Most people would behave in a risk-averse manner over gains and in a risk-seeking manner over losses. Now, graphically and mathematically, this is the same as saying every unit of additional gain worth less than before, while every additional loss feel less painful than before. So, the first $500 makes you very happy. The second $500 that adds up to 1,000, not so important. So, you're okay with just getting 500. What about losing money? Losing the first $500 is very painful. Losing another 500, not so painful. So you are willing to take the chance. Graphically, so this has got diminishing sensitivity, and graphically, it says that the utility function is not just it's concave at the positive part and convex in the negative part. So I think I have it in the next slide, but just to write here, it looks like this. Okay. So this is utility. This is money. Like when you're gaining money, you have a concave function, so you behave in a risk-averse way. But when you're losing money, you have a convex function, so you're behaving in a risk-loving way. So you have this S-shaped curve. So, for example, maybe you can model this easily with just a log function. A log function in the positive region, a negative log function in the negative region. So that would work. Okay, so I have it here. So notice for this diagram, to capture the fact that losing is more painful, the negative side goes down steeper, and it versus the positive side. So it's steeper. The slides will be online. The slides will be online tonight. Okay. Another set of questions. Would you prefer $3,000 for sure versus $4,000 with probability 0.8 and nothing with probability 0.2. So $3,000 for sure versus 80% chance get 4,000, 20% chance get nothing. What would you pick? This one is harder because the average value is not the same. Okay, who's going to choose the first? 1, 2, 3, 4, 5, 6, 7. Oh, 7. Okay. So that's 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 7 to 3. What about this pair? 3,000 with 25% chance, 4,000 with 20% chance, and nothing with probability 80% with 80% chance. So this time around, it's quite a bad deal because it's a much worse situation because you don't have a sure option, or the highest. Well, all you get is a 25% chance of getting $3,000, and which means a 75% chance of getting nothing. And then you have a trend versus 20% chance of getting 4,000 and 80% chance of getting nothing. Now, how many of you would choose the first one now? 0. Reasonable. Okay. It's very reasonable in the sense that the vast majority of people would make the same choice. But you're all being irrational according to expected utility theory. Why? Now, okay. Let me try again. Okay, so U3000 bigger than U 0.8, U4000 plus 0.2 U0. Multiply both sides by 0.25 and then add 0.75 U0 and you get 0.2 U4000 plus 0.8 U0. Okay, so it's actually very simple to show in expected utility. If you prefer $3,000 for sure over 80% chance of getting 4,000, you should also prefer 25% of getting $3,000 over 20% chance of getting 4,000. That's just the property of an average. This experiment suggests that people are very sensitive to change in probability from 1 to a small number, but much less so for changes from one moderate probability to another, even if the change is proportionally identical. When I tell you $3,000 for sure, it does have a particular attractiveness, right? For sure. If I just tell you it's 95% chance, it will feel very different. For sure has a very strong psychological effect. Finally, which of the following would you prefer? Now, $5,000 with 0.1% chance. It's very small. It's intentional. $5,000 with a 0.1% chance. And $5 for sure. Now, the average is the same, right? The average is the same. Which one would you prefer? 5,000 with 0. Wow! 1, 2, 3, 4, 5, 6. Yeah. Okay. It's actually quite reasonable. 6 over 4. 6 versus 4. What about this one? Losing $5,000 with a 0.001% chance and losing $5 for sure. Who picks the first one now? 2. 1. 2. Okay. 2 over 8. All right. Now, what's the problem here? What's your choices are telling me? In this case, very few people are willing to take risks with respect to the loss, and very few people were really a lot of people were willing to take a risk with respect to the gain. Which is exactly opposite of what we did a few slides ago. What changed? The probabilities changed. So, as I said, the pattern we have here is actually quite common. 72% get, in a published experiment, 70% of people picked 5,000 with a 0.001 chance over the case with $5 for sure, and 83% picked losing $5 for sure for the sex instead of taking a chance. But isn't people supposed to be risk averse over gain and risk seeking over loss? And to explain this behavior, you have to think about whether people can actually comprehend what a 0.001 chance means, right? 0.1% chance. I mean, we all understand numerically what 0.1% chance means. But can we really appreciate how unlikely that is? So the lesson is people tend to overweight small probabilities and underweight large ones. So when you tell them a probability like 0.5, they understand what it means. They act like it's really half and half. But when you tell them big numbers like very close to 1 and small numbers close to 0, then they behave quite differently. So what we build based on running a lot of these kind of questions, what you will see is a pattern like this: is that if you give relatively large probabilities, people behave as if they're not that large. So if you tell them there's 80% chance of winning, they would behave like there's only 70% chance. But the exception is 1. When you tell them 1, they understand it's 1. That is, if you tell them for sure, they understand it's for sure. They don't act like it's only 95%. 1 is an exception. So now the reason why the line is continuous is that actually there aren't that many data points. It's not plotted by continuous data points. It's more like 1 point here, 1 point here, 1 point here. So it's possible that this line actually extends like that and goes up. It's possible. Similarly, for small numbers, when you tell people, oh, there's only a 1% chance. There's only a 1% chance of losing. They behave like there's a 5% chance or even 10% chance. What's a good example? The effect of Fukushima nuclear leak. The chance of you ever getting harmed by the radiation from Fukushima, it's so small. It's not smaller than the chance of winning the $5,000 just now. But people behave like it's 20%, right? People avoid going to Japan. The whole Japan, not just Fukushima, right? People avoid going to the whole Japan for fear of getting harmed by the radiation. That's a very good example of this behavior. In fact, this diagram is from the original Kahneman paper. As I said, they don't have continuous data points. Based on newer studies, these days, psychologists and behavioral economists believe this is really more like this. People understand no risk is no risk. 0 is 0. But as long as you have a tiny risk, they behave like it's very big. So as I said, Fukushima is the perfect example for this. The chance of getting affected by radiation is so low, but people nevertheless avoid going to Japan. Okay? So this is probably what really people have in mind. Okay, so we are almost there. The three components combined it. 1, people hate loss more than they like gain. Okay, people hate loss more than they like gain. That's loss aversion. Second, they are risk averse over gain and risk seeking over loss. And third, they overweight small probabilities. 1% feels like 5%, 5% feels like 10%, and 90% feels like 80%. So they overweight small probabilities, underweight large probabilities. The three components together is called prospect theory. And this is the cornerstone of behavioral economics. It's one of, I would say, one of the top three theories. It's the top one. If you need to pick one theory that represents behavioral economics, it would be prospect theory, because it is the strongest explanatory power of many behavior that simply cannot be explained by standard economic theory. Right? So I'm going to stop here today. Next week we're going to talk about what you might want to use as the reference point, because the reference point would affect behavior, and we'll see some empirical studies which looks into what people's behavior that's quite well explained by prospect theory, and then we also do a numerical example to see how it works. All right, so we'll see you next week.